The basic unit of a deep learning model is an artificial neuron. Let's look at how a neuron works by going through the simulator I built in Google Sheets. You can make a copy of the simulator into your own Google Drive and run it in your account. Pretend that we would like to decide if we should approve a customer's loan application based on 3 factors: age, gender, and income. Let's move over to the single neuron tab and take a look at this artificial neuron. Let's move over to the single neuron tab where we see a neuron laid out in an spreadsheet format in this top portion of the spreadsheet. In the lower left portion, you will see a data set with 16 records. If you scroll down a little bit, you will see a total of 16 records. And let's pretend that these are values for 16 customers. We know these customers' age, gender, and income, and these are historical records, so we also know if their loan applications were approved or not. Keep in mind that computer models only compute numbers. So instead of talking about how old someone is, female, male, and the actual income level, we have to convert all this information into numbers so that the computer can compute. So the first thing we do is to represent these features as zeros and ones. Take a look at this data dictionary to understand what these numbers mean. We coded age as 1 if the customer is old, 0 if the customer is young. We coded gender as 1 if the customer is female, and 0 if the customer is male. Income is coded as 1 if it's high, otherwise it's a 0. And for the loan application decision, if the loan was approved, then the customer gets a 1. Otherwise, it's coded as 0. So let's go back to the spreadsheet. And you can see that in the upper portion of the spreadsheet, this is the computation of a neuron. And we have features on the left-hand side. Right now, before we start training, all the numbers are 0, 0, and 0. And all the weights are 1, 1, and 1. And there's a bias value over here, which is set as a constant at negative 0.1. This activation function, which is the heart of the artificial neuron, is a weighted sum of the features. So the features multiplied by the weights and added together, plus the bias term. You can click on this activation cell and you will see this is the equation, which is this feature multiplied by this weight plus this feature multiplied by this way plus this feature multiplied by this way. And then at the end, we added the bias term. This total value is then passed into what we call an activation function. Here we have implemented the step function, which is a simple if statement. It looks at this value and then it returns a 1 if the value is greater than 0. Otherwise, it returns a 0. Because our activation value right now is negative 0.1, this cell returns a 0. And this is actually what we call the predicted class or predicted label by this neuron. The neuron has essentially predicted that this customer's loan will not be approved. However, we can also compare this to the actual class. The actual class will be the actual answer from the historical record. And that number will be copied over here. And then this equation will compare if these two numbers are the same or different. If they are different, then there will be an error. And you can look at this error term is literally the actual class minus the prediction. And then over here, the model will use this equation, which is the learning rate times the corresponding feature value times the error to produce a number that we will use to adjust the weights in the next iteration. Now let's click this train button here. When we click train, this button will copy the first customer's records up here for feeding into the model. And then the model will do this weighted sum calculation, pass it along into the step function, and then compute this error. This error will then be used to compute the changes that we will make to the weights in the next iteration. So let's take a look. So this button is running a script that I wrote behind the scene, and it's basically just doing some copy and pasting. It's copying 100 up here and then doing these multiplications and additions to produce an activation value of positive 0.9. And this gets passed through the step function, which produces a prediction of 1. However, we have also copied the actual class here, which is 0. The two numbers are different, which produces an error of -1. And this error is multiplied with the feature values and also the learning rate of 0.2, which is just an arbitrary number that I have chosen previously. And then these three numbers will produce a little value, which we will use to adjust the weights later on. Now, since the second and the third features are 0, anything multiplied by 0 produces a 0. So these two changes will be 0. Only the first weight will get adjusted in the next iteration. And the next iteration, the weight will go down. The weight for age will go down by 0.2. So the next iteration, the weights should be 0.8, 1, and 1. Let's see if that's what happens by clicking the train button again. So this iteration, it copies the second customer, 101, up here, and then made some adjustments to the weights. Again, we have produced an error. So far, the model has been producing nothing but errors. And these errors will be used again to calculate weight changes for the next iteration. Over here, you will see a red circle. This is actually a pie chart that's being produced to illustrate the number of errors versus the number of correct predictions. Because so far, we do not have any correct predictions. It's 100% error. So you're seeing a full red circle here. Below the circle, the pie chart, we also see a line chart, which plots the error rate against a timeline. So for the first three iterations, the error rate has been 100%, 100%, 100%. So we see a flat green line, a flat red line that's being produced here. So let's continue the train. Whoa, our model made the first correct prediction. Look at that. So this correct prediction is colored in green. And as you can see, the neuron has been making the same prediction 4 times. It's predicting 1, 1, 1, and 1. But due to pure luck, the actual correct answer switched from 0 to 1 in the 4th record. So we actually have a correct prediction here. One thing I want to highlight is that when we have a correct prediction, the error term is the difference between these two numbers. So the error is actually 0 now. And see what happens when there's no error. Well, the model will stop learning because it's no longer going to change the weights. Anything multiplied by 0 becomes 0, so the model will stop changing weights. And when you stop changing weights, you stop learning. But does that mean that our neuron already knows how to solve all these problems? Not so fast. because even though the weights are not going to change, the data is going to change. The next customer is 100. So let's try again and see what happens. So we didn't change the weights, but we got a new customer, and this prediction of 1 again is an error because this customer's actual class is 0. Again, we have made an error, but the good news is that error is going to propel the model to make some changes. And as you probably have noticed by now, when the model's weights are changing, that means this neuron is learning. So we'll train again. Oops, the model made another error. As you can see, the error rate went down a little bit and it's picking up again. But that's okay. The error will continue to motivate the model to change the weights a little bit and try again. We got another error, so let's try again. Finally, we made another correct prediction. Again, as you can see, when we make a correct prediction, the model will stop learning. There will be no change to the weights, but fortunately, we'll get another customer whose data hopefully will get the model to move a little bit. So let's try again. Oh, another correct prediction. Let's try again. Oh, an incorrect prediction. So let's try again. Another error. Oh, another correct prediction. Another correct prediction. And just like that, our little neuron figure out the magic combination of weights that would be able to solve all these problems. As you can see, the error rate went down and picked up a little bit, and then finally the model was able to continue to make more and more correct predictions toward the end. I hope that you find this simulation to be insightful and useful in terms of illustrating the learning process. As you can see, the model started with equal weights, which assumes that these features are all equally important. In other words, the model doesn't actually know which feature is more important in terms of predicting loan application approval. So it just starts with an assumption of equal weights. But through this iteration of adjusting weights in response to the data values, the model was able to start from making 100% mistake to 100% accurate over the course of just a couple of minutes. Thank you.